Okay, so I'm going to do another case study because I want to illustrate a thing called over dispersion. And roughly what this means is there is more variability in our data that can be explained by logistic regression. Okay? And so we'll look at an example to try and illustrate what I mean by that. So the one we're going to look at is called cells. So what the setup is they wanted to see if you could kill cancer cells by radiating them. So the experiment is they would take a dish and they would place 400 cells. And they have a lot of these dishes and they would irradiate them in batches. So they'd take 3 of these cells and put them in and they would irradiate them. And that's it. And then they would measure how many cells survived because they want to get the dose right. But to have a control, what they did is they said, fine, what we'll do is we'll take a load of these batches, we'll put them in the radiation chamber, but we won't switch on the machine. Just so we can get an idea of how many cells are just going to die anyway. What we call natural mortality. So what we've got is we've got which batch it was. So we've got 9 batches all up. Remember they had no radiation at all and we want to know the number of surviving cells at a 0 dose. And the idea is that we should be able to model this as if I is the, now I'm trying to remember, now I've lost track. I think is the batch and J is the replicant within the batch. Oh yeah, here we are. I got it written down here. So I is the batches, so I goes from 1 to N, so 1 to 9, and J is the replicants in each one. And we think there is going to be some pi I, some batch type thing. Okay, that seems fine, that's good. So what we'll do is we'll read in the data and have a look at it. And what we got is, here's the first 3, they're all from batch 1, and here's how many cells survived. Do a quick EDA just to check there's no missing data, which is always good. Seems reasonable. And the other thing I like to do, as you know, is I'm going to create basically a proportion that survived. We know that n equals 400 each time. We've got a factor batch. So if I do my plot here, what we see, well, the first thing we notice is they're quite closely clustered within each batch. So each of the x-axis is a batch. But there's a lot of variability, isn't it? You know, up here, you have about 50% survival rate. Well, this one's down to about 0.2. So there's a lot of variability in this data. So looking at this, I'll be thinking about overdispersion. Well, let's do a quick illustration of how we can measure that. So let's think about a model. Let's assume that all the batches have the same survival rate. Okay, so I'm going to aggregate the data. So I'm going to say yi is going to be a binomial distribution. The number of trials is 400 and the probability of survival is pi. Yep. And we know that the expected value of y will be 400 pi. So I'm going to do, we've done maximum like estimate and stuff like that. I'm going to do what is called the method of moments. So basically, I know what the expected value is, 400 pi. I can get the sample mean, so I can basically say that pi hat is going to be the expected value of yi over 400. And I'm going to replace the expected value with the first moment, which is sample mean. Which sort of makes it, if you wanted to estimate the proportion, you'd count in total how many survived. So here's the mean of the survived. We divide it by 400 and we get a proportion that survived of 0.3276. Okay? And if we actually look at the mean of the proportion we calculated, it's the same, just as we expected. Now you might say, well, actually, I don't want you to do that, Jono. I would like to use fancy logistic regression. So let me show how you do that. You could basically fit and say there's no batch here, there's just an intercept. Fit your model. So we've got survived, failed, which is 400 minus that. Data equals cells, family equals binomial. If I fit that and then I look at my intercept, I get an intercept of minus 0.7187. That's the log odds, the overall log odds. So we undo that and I pretty well get the same number. Okay, so we think for the overall, if we have a common proportion probability of success, it should be 0.3276. Well, easy. From your binomial, you know the variance should be 400 times pi times 1 minus pi. We don't have pi, so we put the next best thing in, our estimates. So we can do that calculation, and we expect the variability in this data should be 88.1. What is actually the variance, the true variance? 1,670. You can see there's huge amounts of variance compared with what we expected. So the problem is in this data, we're having a huge amount of variability in survival compared with what we expect. So this data is over dispersed. There's more variability that can be explained by a very simple binomial model. Now, you might say, well, look, Johnny, you didn't take into account batch. Take into account batch, it will solve all your problems. That's where the variability is coming from, the batch. Fair call. So let's do that. Let's fit a model where we now have batch in there as well. So we fit it and we look at the summary. First of all, we notice that yes, you're right. Well done, you lot. That batch is significant. This is all compared with batch 1, and we find that a lot of batches are significantly decreased compared with batch 1. So is it looking good? Is it fine? Well, let's look at this residual deviance. We've now taken into account everything we can, everything we have in this data set. The only information we had was batch. We've put that in, we've taken it into account. So now let's see if there's a significant residual deviance by using our 1 minus value. Yes. So if you think about it, we've sort of put everything in, and our residual deviance is still significant. It's still not explaining everything. And in this case, what it's not explaining is all that extra variance. There's not much we can do at this point with this data using logistic regression. We need something that somehow can have more variability. If you think about it, the whole problem here is these two parameters are ni and pi give us both the mean and the variance. You need something that can almost increase the variance. And there's a couple of ways of doing that, and the classic one is you use a quasi-binomial. A quasi-binomial is a whole new model that is sort of like an expanded version of binomial that can have extra increase of variance. I'm not going to do that here. That's a bit more advanced for what we're doing in this course. But if you are interested, go and look at the quasi-binomial for dealing with over dispersion. Okay, that's it. See you next time.